Okay, can we start?
Yes.
Okay. Good afternoon, everyone, Mr. Jati and everyone. Today, our group are going to present about deriving transfer function from Bode plot. Myself, me, is Kenneth with Anissa and Anthony. This is our group, yeah, the group 2. First of all, we are going to tell you about what is our outline of the presentation. First of all, First of all, we need to know what is the general step to find the transfer function from the Bode plot. First of all, we need to examine low frequency behavior to determine the constant gain, and then we need to identify the slopes, and then we need to analyze the high frequency behaviors, and last but not least, we need to write the transfer function. Now this is the review of the Bode plot. This is in general an open loop transfer function will have this following form. This is the FHS equals to this. Yeah. Now we are going to see this is 6 cases for the open loop transfer function. This is the first case, this is the second case, the third case, the fourth case, the fifth case, the sixth case. The first case is the simple pole, the second case is the pole at origin, the third case is constant gain, the fourth case is simple zeros, the fifth case is complex conjugate poles, and the sixth case is complex conjugate zeros. So this is the magnitude plot for each cases, which included the behavior, the breakpoint, and the slope, and this is the phase plot, the P. This is the decrease for how many degrees. Like for example, the simple pole is decreases from 0 to minus 90 degree at breakpoint, and for the magnitude plot is like we need to know the magnitude behavior. So for example, like the constant gain is we use 20 log 10k and so on. So this is once again this is the table, yeah. Now this is the sample of the simple pole and zeros and complex conjugate. This is the zeros and poles for the simple pole and zero. So it's like this, but for complex conjugate it looks like this.
So basically what we are trying to explain here is for a zero, you can see that the value of the slope is always positive. The only difference between the simple zero and also the complex conjugate is the number of is how much the slope is. For the simple zero, it is plus 20 dB per decade, while
Yes.
the complex conjugate is plus 40. For the poles, you just need to flip it.
Yeah. So for zeros is going upward, for poles going downward toward the negative. Yeah. So this is the role of constant gain K and poles at origin. This is the original Bode diagram. This is from 0 and it's going downward toward the negative direction.
The transfer function is 1 over x plus 1. Actually this I want to illustrate how the K and the pole will fix. So not yet deriving.
This is not
Or the original. And with the gain, K is for one. What the flow with the yeah. So basically what we're trying to explain is with the gain K, you shift the plot by some value, and with the pole into this, you add slope of the
Yeah.
So next to an example problem. By observing it like this, you guess what kind of is it a pole? Is it a zero? Yeah, it's a pole. So
Right.
That's
first, let us analyze the slope. How do you find what is the value of the slope here?
Yes. Like that. If it's 90 degrees, your blind is minus 50.
In this case, we try to use a formula. So the slope is simply the difference on the magnitude over the difference in magnitude. Let us Can you see what? Can you read it? So here, the slope is delta over what is the difference between the decibel here? Can you see it? Can you see it? Let's analyze at this point, yeah, where the slope is. Yeah, -3 and yeah, around -20,
yeah.
right? How about to determine the decade? How do you do?
When that means
How about using formula? Do you know how to do it?
it's here.
Yeah, you can see it that way also. But what I do is out 10 and this way. Yeah, it's also work like that. But yeah, that's the very proper way.
This one minus 20.
Yeah, let's just yeah. Yeah. So let's input the numbers here. Since -3 is located at 10 to the power of 1. So let's write it here. 10 to the power of 1. And -20 is at 10 to the power of 2. And do you want to try using the calculator? See? Let's calculate together. And this one? Oh yeah. 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 So it's around 17 dB per decade. You can approximate this to around 20, I think.
Yeah.
So here I approximated around minus 20 dB per decade. Everyone okay with this?
Why
Okay.
we should approximate?
Because if you remember here, the cases are either 20 or 40
Yeah.
for the slopes. We don't have 17, right?
Yeah.
The closest one is to 20, so approximated to 20.
Long as kelipatan low.
Yeah,
Or
yeah, for all cases, or no slope delta. Now let's analyze the breakpoint. Breakpoint is where the slope starts. Where do you think is the breakpoint? Yeah,
The one negative 17, why can you split?
because remember in here we don't have 17, right?
Yeah. So we
Is-
round it up to the nearest one is 20.
It's like that.
Yeah, it's kelipatan
So
20.
Ya,
Ya.
ya pokoknya 20, 40, 60, 80, 100 dan seterusnya.
Ada.
Baik ya.
Sekarang tes juga.
Ya, continue ya, continue. What about breakpoint? Where do you think it starts? Remember for a pole, let's go back here. Breakpoint starts when it's around 3, minus 3, negative 3. Where does negative 3 here? I already put
One.
it's a case 1, yeah. So here, in a case 1, you know that the breakpoint is located at 1 over t. So we write it like this: 1 over t equals to 10, right? Yeah, 10 to the power of 1. You solve for t, 1 over 10, and t becomes 0.1 lah. Salah. Yep. And for a simple pole, this is what it looks like, right? 1 over this.
It is like
T is that a constant.
Time constant. Time constant.
So how does the transfer function look like? You just put it. You just put the 0.1 to the. That's our transfer function. T is a constant for that constant. Yeah, 1 over omega. Okay. What about this one? What about this one? What do you think?
Is no slope. Start from origin.
Let's see. Does it start at 0? No. So most likely you have a gain or yeah. Remember that? Yeah. Let's try to analyze different sections of the plot here. Before we analyze before and after. Yeah. So before 0, we can find that the slope is minus 40. Do you want to calculate or calculate? Let's. Yeah.
However, for the full X, when you have one full X, have constant minus. Because we start at minus 1. Of course, I can put start at and another this minus.
So basically, yeah, what we get is before the breakpoint, our slope is minus 40, and after that is minus 60. So what we do here is you actually add minus 20 dB per decade, which means there is a simple form. So it's a case 2 with case 1. Okay, sorry. When I actually analyze it separately, sir. So before the slope change and after it.
Breakpoint.
At 1. 10 to the power of 0. 1.
Oh yeah, okay.
This.
Yeah, yeah. Oh, breakpoint. 1.
Yes, sir. Breakpoint at 1.
Who wants to affect partners? Four and zero. Just like the constant and percentage when you have the pole, you know that there is an angle of gravity.
Okay, sir. So if my method was I use the magnitude plot. So in here, we know that for a case for a pole at origin, it's given by 1 over s to the power of n. Now we're trying to solve for the n. We know that the slope that we obtained was minus 40. So for a pole at origin, this is what the slope looks like, minus n times 20 dB per decade. So n in this case will be 2. You have 2 poles at the origin. So the transfer function for the pole at the origin becomes 1 over s squared. This is for the pole at the origin only. For the pole at the simple pole, we use the same method as before. We know the breakpoint is at 10 to the power of 0, which is 1, and we try to solve for t. From here, we can get, this is what we get from the pole at the origin, right? And this one. For the simple pole, you just plug in t to be 1. And our combined transfer function will be,
How do you get
because we know the breakpoint at 10 to the power of 0 from oh no, I use the magnitude plot. I know that when I calculate this part and this part, there is a change in the slope. So I know that there must be a breakpoint at that point. Yes, sir.
Yeah.
Yeah.
Another thing this is what I want to ask. When you have the double pole at the origin, you have constant minus 1. Then when omega is equal to 1, then magnitude is 0.
Oh.
So when karena one person or one
Yeah.
There,
point it out. That's the problem.
the simple pole case.
If the point is greater than 1, then have confidence.
This is for the case 3.
This is Anthony's part actually, sir. Should I proceed or?
Now, just explain it first.
Okay. So for here, as you can see, for this Bode plot, does it start at 0? No.
No.
But so most likely it's either there exists a gain. Yeah. Yeah. Yeah, it has to be some constant over there. So this will be, well, case 3, constant gain k, which is because of the shifting over there. Wait. Oh. And to find the k for a case 3, you use the top formula.
Yeah.
20 log 10k, which corresponds to 20. Yes. Oh, which one? The previous? Because remember, in a case of a simple pole, that the breakpoint happens at Oh.
Why?
no.
Kalau sebelum saya kan itu, ada ada
Wait.
mungkin lagi saya tadi untuk pakai dulu dan modal so we are on the base 0 dB or 1 or at 0 so it is placed back
Where is that from? Not that. What is the reason?
the extra portion
Berarti kalau ada di korpo, saya bisa
And back to case number 3, after you solve for the k, you know that there will be a gain of 10 in your transfer function. And this is actually just continuation from our case 1 previously in this one. But you simply shift it by 20 upwards. Therefore, our transfer function, you just multiply 10 by the case 1 previously.
Now this one.
Yeah, for case 4,
Simple zeros.
simple zeros.
So this is, you see what is the difference with the last the recent cases? What is the difference with this stuff? Correct? That's right. So if this is rising, yeah, so the slope is also positive. Look at the slope.
because it will up
You know that this over here, when the frequency is this 2, yeah, 1, 2.
Yeah.
If you use the magnitude plot, you can see that it's around 3, right? Around 3 dB per decade. Around 3 dB. Yeah. Here Anthony tried to use the phase plot. Yeah. From here you know that the breakpoint is at 2 and solve for t, and you just put it into the simple zero case and you will get the transfer function of this. Yes. Well, Uh,
It's decade.
oh, what is decade?
It's supposed to be the next.
Yeah, this decade. So from here to here, 1 decade.
Yeah.
From here to here, another decade. Same. Same. Okay. Now is for case 5 and 6. If you remember that case 5 and 6 is a complex conjugate and you will have this kind of shape. Just depending on the value of zeta. As zeta is smaller, you can see the dB becomes very high.
Yes.
And as zeta is equals to 1, it looks like the simple pole case in this. This is one example for case 5.
As you can see.
Wait. So, yeah, I don't know how to determine the zeta self for this case. This one.
Try for plug again. Put it
So basically trial and error, sir.
right. Same thing for your driver. So you estimate another data.
Yeah, I think what Anthony trying to do is for K6, and he tried to estimate zeta.
But
I'm not sure actually, sir.
but you know that the transfer function is this one, right? And sorry. So you know what's the frequency in there? Coming from the phase plot, you know what's the frequency, right? Okay. And then from here, you can get it starts from 0, yeah. The magnitude is 0 in the low frequency. So 1 in here, and then you have s squared plus 2 zeta omega s plus omega n squared. You know what's the omega n? You put it in there, and s you replace with the j omega. Okay, this j omega square. What's the omega in there? 3. Okay, so you have 3 j omega and then plus 3 square. You find out what's the magnitude. Okay, get the magnitude. So what happened in here, j omega square, it becomes minus omega square. This one become, this is 3 also. Oh, sorry, 6 zeta j omega and then plus 9. We know that the omega n is 3, and then we want to check the magnitude at 3 radian per second, right? So we put omega equal to 3 radian per second also. Okay. Omega is 3 radian per second. Substitute in here, so you will have minus 3 square then plus 18 zeta j plus 9. So you only have the imaginary part in here, yeah. So it becomes 1 over 18 zeta j. So the magnitude of at 3, yeah, this is 1 divided by square root of 18 zeta. You square it, of course. Okay. So what's the dB in here? What's the dB? Can you get it? Minus 5.93. Okay. So in here, 20 log of g of j times 3, this is equal to minus 5.93. You find out what will be the magnitude based on this. Can you get it for me? No, not this one. This one first. 20 log of something is minus 5.93. Okay. 20 log of m is minus 5.93. What is m? 0.505 lah. Okay. So we know that 0.505 is equal to 1 over this one, yeah, square root of 18 zeta square. So I have the zeta in here and then square root of 18. Yeah, then my zeta will be 1 over 0.505 square root of 18. What will be my zeta? In here, 0.47. Is it really?
Yeah.
Yeah. So that will be the zeta, theoretically. I don't know how he estimate that, but yeah.
So it will convert the minus 1.93 because it is
Still in dB. Yes.
Yeah. So what's the unit of
Oh, the m, it has no unit. It's unitless. Because m is the ratio between input and output. Okay. So back again. Then for the experiment, you can do trial and error.
Okay, I do photo first. Now I want to talk about the problem here. One of the problems. This is the Bode diagram, the example of the Bode diagram we're going to solve.
So first, let us identify. Do you think there is a constant k in here? Yes. What about the slopes? It's a bit tricky. Yeah. So yeah, because I'm using the magnitude plot, so I divide it into several sections. We know that over here,
zero common because one cannot see the system that's
Oh, yeah, yeah, yeah.
not see the base level.
Yeah, I have made it so.
Yeah, yeah.
Dangerous.
Yang itu yang buat box kan.
Ya, ini punya ya. Is it the same?
Okay. Let us have the floor to say what do you think? What? Yeah, I mean, what is it from here? Oh, the
Plus 20 dan minus 40.
The plus 20 is correct. The minus 40 correct, but not really correct. You already know the answer. No. Yeah, you already know the answer.
Why not right?
Almost.
Yeah, almost.
Ya.
There's a zero.
Oh.
Minus 20 apa tuh Niki? Minus 20.
Yeah.
Oh, minus 20.
Yeah, you want to say, oh, minus 20, minus 20.
Ya.
Oh, karena
Dari kuning ke ini. Oke, satu ini.
Yeah. What?
So we will have
Constant gain at minus 20. Constant gainnya K, you mean? You mean the K? No. No. Yes. One simple zero, yeah, and two simple pole. So in this case, we have a gain, we have one simple zero, and two simple pole. This is the gain. The gain is making this kind of shape. The first peak, the first slope you see is because of the zero. If you see it like this, perhaps you might think that there's nothing happening here, but there's actually an addition of minus 20, slope over here, and this is another addition of minus 20. Yeah. Yeah.
they're going up, right? But then you see in the middle, it comes straight. Why it comes straight? Because there's an addition of 4 minus 20 plus. You know that is minus 20. I mean, like this way it becomes straight. Normally, if you just have zeros, it's going to be going up. But here it's straight, so there has to be something straight.
Kan nggak susah saya. Kita main 20 kan. Kalau ada poin ya from the yang atas kita ambil yang hitung gradient biasa aja gitu. The magnitude
Detik satu tiket.
ya
Tapi menurut tuh tiketnya kan mulai dari antara negatif 5 dan 0 terus di akhir sama. For example, like you see minus 20 and minus 5. Minus 20 minus 5 over then 0 minus then 1.
So what I do is when I try to solve this is I approximate it. So because of the 3 dB is kind of making a confusion here. So I approximated it where the break when the break point where I kind of removed the 3 dB over here.
Yeah.
So
Thank you.
if I draw this like over here, you have a constant gain K and what is this? 1 ya, 1 and 100. So after 1, which is where the yellow and red lines intersect, you have a plus 20 slope. And after between the red line and the green line, you have this. To make this kind of shape, you must add plus 20 slope with negative 20. This is 0, no slope right here. 0 slope. So from here to here, minus 20. Yeah, right? And just simply go down by another minus 20. Yeah, that's what's happening here. Now let us. Yeah, we already. I try to calculate what's the slope over there, and I get this value plus 20 and minus 20 corresponding to that.
Yeah, magnitude over decade. Decade is like
Next is how we construct the complete transfer function. Let us start from so what's happening firstly you have a K, right? Yeah, thank you. And at omega equals to 1, you have a slope of plus 20, which means that you have a simple 0. At omega equals to 10, what's happening is you add a minus 20 slope, which means that you have a simple pole. And same for when omega is equal to 100, you have minus 20 slope as well. It's simple. So from here, you know that the transfer function the total transfer function, you should have 1k, one simple zero, let's put it as t plus 1, one simple zero, simple whole plus 1, and another one over here, T3s plus 1. Now let us solve for T1, T2, and T3 first. We know that T1 is a simple zero.
Yeah.
A simple zero. If you use this kind of shape, you know that the breakpoint is over here, right? This one. Yeah. So breakpoint. So yeah, 1 over t, t1 equals to 1, and t1 1 over 1, 1. For t2, yeah, 1 over t2. So for t2,
1 over 10,
3.1, and for t3,
100.
100. t3 is equal to
1 over 100, 0.01.
0.01. Then you plug it here. How about the k? Yeah. Use what formula? This one. 20 log 10.
Equals to
20 log 10 k is equals to minus 20 log 10 k is equals to minus 1. Solve for k. How do you solve for k? Calculator. Yeah.
Kita ada di reflection awal.
Yeah, this is what I do to solve for k. Rewrite it in exponential form. Yeah. So I get 0.1 for the k. And then we simply plug in everything. This one.
Log, yeah,
Log A, log A,
0.1.
Log B.
Ya, log B.
Apa aja dengan B?
Ah.
Yeah, this is exponential form. Ini pangkat ini equals to ini. Ya.
Ya, log A.
terus oke kan?
Log B dengan A. Apa aja dengan B?
Pokoknya
Ya, mau itu lah.
kan oh no Parai. Ya, tunggu.
Ya. Oke, right. Then we just plug it to the transfer function. 0.1. T1 is 1. So S plus 1. T2 is
0.1.
0.1.
S plus 1.
S plus 1. And T3 is
0.01.
0.01.
S plus 1.
Yay.
And that's okay in that form. In that form is okay.
Dia di
No, that is in the border form, right? So that is sufficient. The last part over there is in advanced form.
Oh.
In exam, we use Bode plot.
You need for Bode plot.
It is easier for you to get the transfer function in Bode form from the Bode plot, of course. So just put in the Bode form, that's okay.
Oh, Evans kan kamu perlu.
Okay, Anissa, that's a good example. Okay, so I hope next group for Wednesday also do the same thing like this. Okay, so no more confusion on the minus 3 dB, yeah, please. Yeah, yeah. So I also want to say something about our agreement. Yeah, when you are asked to plot the Bode diagram, you are plotting it like this. Yeah, you don't have to put the curve for the minus 3 dB. You just put it like this. So I know. Yeah. So I know when the slope starts, when the slope ends, okay, and how much the slope is. Okay. Yeah, because when you want to do the curve, that goes to a very detailed border plot. Okay. So we are just doing the sketching, which makes your exam to be easier also. Yeah. Okay. If I put border plot as one of your exam problem.